Okay, this is TempleOS 5-minute random code walkthrough episode 9, and I'm Terry Davis, your host. And we're going to do a random code jump. Okay, expand buffer. This is in the kernel compression routine. Basically, this is an LZW compression. There's a arc compress is a structure, and this is not the arc control. This is compress. Okay, this is the when you call compress buffer, it gives you a pointer to a chunk of memory that has the compressed data, and as part of, there's a header on that compressed data that tells the size. So if you compress data, then you probably want the size of the chunk you just got handed, and so what you do is you it's a arc compress structure, and it has compressed size and expanded size. So the only interesting thing is if you want to do a partial compress to do part of a buffer and then do some more and then do some more in multiple pieces. If you want to do multiple pieces, then you create an arc control, and well, let's see. I guess we would talk about compression. Actually, you can do compression or expansion. And how does this work? I think you have to set the finish compression. I think you have to set a pointer. I don't remember. Look at it. Anyway, you compress it in a partial buffer, and I think you have to tell it the partial buffer size. And so I just compress whole files at once. With compress buffer compresses a whole file at once, and expand buffer expands a whole file at once. So it doesn't do partial. It doesn't do a stream, a pipe. It doesn't do a pipe. It doesn't do a stream. It does a whole one. And if you want to know what LZW compression is like, basically what it uses is a LZW uses a table, and let me see if I remember this. Let's say you have A, B, C, C, B, A, B, C. What it does is it sticks A in a table, then it sticks B in a table. No, it builds up a string of at the offset of it's got the 256 lowest values have the single character, and then when it starts getting A, B, it adds an A with this adds an A with a B with a C. This adds an A with a B with a C. I don't remember. I think you get an A, B, and then you get an A, B, C in your table. It goes 12 bits. So the first 256 are single character, and then it goes up to what's 12 bits? 4096. That's the maximum table size. Each time it adds one, it adds to the previous one more letter, something like that. I don't remember. All I know is that you end up with an AB, then you end up with an ABC, and anyway, so the C version is right there, and then there's the assembly version. I did it in assembly just because I want it fast, even though when I hand assemble, it's not as good as GCC probably, but it's better than my compiler. So don't hand assemble if you have a good compiler. If you have my compiler, you might want to hand assemble. Anyway, there's a slight there's a trick. If it finds all characters are less than 128, then it uses. Remember, I said that first starts with 256. Well, it starts with 128, and it anyway. If all the if you only use the 7-bit ASCII, then it starts with 128 size table or something like that. So anyway, I originally did this when I worked at Ticketmaster. Somebody handed me a magazine with LZW algorithm, and this is the algorithm coded. And for Ticketmaster, I did a multiple file archive. This is just a single file, single buffer. You can use this for any buffer. It's pretty nice. I use it in a couple spots. I use it on the graphics file, the GRA file. If you had 24-bit color, you couldn't use this compression. This is good if you have 16 color, because it's byte oriented. This compression is byte oriented. Anyway, so it's good for 16 color graphics. That's 4 bits. Anyway, so that's that.